Hello everyone, I just wanted to do a quick tutorial on complex numbers. So, a brief history about complex numbers. Complex numbers came about because mathematicians were trying to solve the following equation. Okay, so if you move the 1 to the left-hand side, you get x squared equals minus 1. And finally, if you take the square root of both sides, you get plus or minus the square root of negative 1. So the question becomes, what number multiplied by itself gives us negative 1? And the answer is that there is no number, no real number, that can do this. So it turns out that in a lot of advanced mathematics calculations and solutions, this appeared a lot. So mathematicians, they couldn't just ignore it, right? They had to come up with something. So what they did was they said, let's just call square root of negative 1. Let's just call it something. We're going to call it I, where I stands for the imaginary number. Now, electrical engineers, we can't use I because I is the same thing as current, right? So, electrical engineers, we use the letter J. So you can always tell who wrote a textbook, if they're a mathematician or an engineer, based on how they represent the Greek letter, the imaginary number I, right? Either they write it as I if they're a mathematician, and if it's an electrical engineer, you'll see that they write it as J in their textbooks. So this is what's called an imaginary number. I'm going to use J because we're taking an electrical engineering class and we need the letter I to represent the current. So this is an imaginary number. Now a complex number is different than an imaginary number. A complex number has two parts. So in a way, complex numbers are very similar to vectors. Remember when we learned vectors, that vectors have two components, or maybe they have three, or maybe four, or infinite components, right? Depending on what type of problem you're looking at. In the real world, right, in the three-dimensional world that we live in, you'll have a three-dimensional vector, x, y, and z component, right? We learn about this in physics and in math. Well, imagine complex numbers, right? They live in the 2D world, right? Two-dimensional world. They have only two components. Instead of x and y, right, these components are called the real component and the imaginary component. And we can represent it here on an axis, like an xy axis, where the x-axis is the real axis. In other words, all real numbers live on the x-axis, right? 1, 2, 3, so on. Also, all real negative numbers live only on the x-axis. In a similar fashion, the imaginary numbers all live on the y-axis. And imaginary numbers, right, they have the j in front of them. So for example, this is j, 2j, 3j, 4j, 5j, blah, 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 all the way to infinity. In the negative direction, we also have negative j, negative 2j, negative 3j, negative 4j, blah, 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 all the way to negative infinity. So the imaginary number, or unimaginary number, right, will be a number that has a j in front of it. That's an imaginary number. A complex number is going to be a vector that exists in this two-dimensional plane. So for example, let's look at the imaginary number z. Okay, and as you can see over here, right, z is a complex number, and z is not purely imaginary, nor is it purely real. It's a mixture of imaginary and real. Z, right, has an x component, which is real, and z also has a y component, which is completely imaginary. So the way that we would represent this complex number would be 3 plus j2. I know that over here I write it as 2j, but you could also write it as j2. And traditionally, it's written like this, because we want to put here the real number, and behind the j, we always put the imaginary number. So in other words, if I were to write a general, just a random complex number, it would be written as real part plus j, imaginary part. And this format is called rectangular form. So the difference between a complex number and an imaginary number. An imaginary number is just a number that exists on the imaginary axis. A complex number has both a real part and an imaginary part. So that's why it's complex, right? It's not completely real, but it's not completely imaginary either. So let's say that we were to take a look. Let's say we go here to a fresh complex plane. By the way, this C with the funny line through it, that stands for complex, okay? Basically what I'm saying is that the x-axis is the real axis and the y-axis is the imaginary axis. So let's say we just had a random complex number, okay, like this. Let's call that again z. And let's say the real component, we call it a. And let's say the imaginary component is b. So when we write it, we would put jb. So in other words, I can represent z as a plus jb. Let's also consider the angle that this complex number makes with the real axis. We'll call that angle theta. So this complex number z, much like a vector, has a length. That's called the magnitude, right? So the magnitude of z, you would find it just like you would find the magnitude of a vector. It's the square root of the real component squared plus the imaginary component squared. So that is your magnitude. Now I can represent my x component using a little bit of trigonometry. If you see over here, we have a right triangle. And this over here is the right angle. So let me just, in black ink, I will highlight here, if this works with me, the triangle. So this distance over here, right, a, I can write it as the length of my hypotenuse, in other words, the magnitude of the vector z. Let me make this a little thinner. The magnitude of the vector z times cosine of theta. Alternatively, if this is not completely obvious to you, if you remember trigonometry, if you use the mnemonic SOHCAHTOA, right? Think cosine of theta, right? Cosine is adjacent over hypotenuse. So it's going to be a over z, right? So if I were just to solve for a, I just multiply both sides by z, and I get exactly this equation. It's basically a variation of the SOHCAHTOA equation. This length, right, is going to be b, right? Your imaginary component is b. And I can represent it also using a bit of trigonometry as the magnitude of z times sine of theta. So let's write here a is going to be magnitude z cosine theta, and b is going to be magnitude z sine theta. So yet another way that I can represent my complex number z, right, instead of writing it as a plus jb, I can write a as magnitude z cos theta plus j magnitude z sine theta. So z, right, common factor, I can take that out. And I'm left with, in parentheses, cosine theta plus j sine theta. And this equation here has a name. It's called Euler's equation. I'm not expecting you to know what this equation is, so I'm just going to give it to you. Euler's equation is cosine of theta plus j sine of theta equals e to the j theta. I'm not going to prove it. We don't have time for that. Just accept that this is Euler's equation. Okay, it's one of the equations that mathematicians claim proves the existence of God. That's all you have to know so far. So I can replace this cosine theta plus j sine theta with just e to the j theta. So in other words, what I've just shown is that I can write my complex number z as magnitude z e to the j theta. So this is called exponential form. So in other words, I can write my complex number in exponential form. There is one more form that I can write my complex number in, and that's called polar form. So polar form is basically a shorthand. I just take the magnitude z, I draw this angle sign over here, and I put in a theta in the angle sign, right? The theta representing, of course, this theta, okay? So instead of writing e to the j, I just put this angle sign. So this is called your polar form. So the reason we have so many different ways of writing complex numbers is because it's helpful for doing calculations. So for example, sometimes rectangular form is more convenient versus polar form would be convenient in another application. The two forms that we're going to be using the most are the polar form and the rectangular form. We kind of use the exponential form, but we mainly use polar and rectangular. Finally, let's say that we wanted to find the angle theta. Well, theta is just equal to, right, this theta is going to be inverse tangent of b over a. So in other words, to find theta, all I need to do is take arctangent of b over a. So on this page, the equations that you need to remember, this one for sure, these equations as well, and this equation. And of course, you need to know the rectangular form. And these two guys. But mainly, we're going to be looking at polar form. So this is great. We get a basic understanding of complex numbers. But how do we work with, let's say, two complex numbers? Let's say we want to add complex numbers. Let's say we want to subtract. Let's say we want to multiply, divide, so on and so forth, right? How do we do that? So first, let's consider two different complex numbers. Let's consider this one, which is z1. So that's going to be a1 plus jb1. And let's consider this complex number z2, which is a2 plus jb2. And let's, as an exercise, let's write each of these complex numbers in their different forms. So for the sake of time, I wrote out the solutions over here, right? So to write them both in all three forms, right? Z1 is A1 plus JB1. This is our rectangular form. This one will be exponential. This one will be polar, right? And then I just write, Z1 magnitude is given by this equation. Theta 1 is given by this arctan equation over here. And likewise, you have the same the same business you have for z2 written over here. Okay? So now we're going to consider the operations. So let's consider, for example, addition. So addition of complex numbers is just like vectors, right? We have z1 plus z2. So z1 is, we're going to write it now in rectangular form. It's more convenient in this way. So I have here my two complex numbers, and the way we add them is we literally add like vectors. We add first the real components. So it's going to be a1 plus a2. Then we put plus j, and then we add the imaginary components. So it's going to be here b1 plus b2. Much like addition, subtraction is going to be subtracting the real components and then subtracting the imaginary components, right? So basically, we have the same thing over here, except I have to just replace the sign with a minus, right? So I have here, this is z1, and now I have minus z2, right? So the solution is going to be the real components. I take a1 minus a2, so it's going to be a1 minus a2. And then I have my imaginary components where it's going to be b1 minus b2. Like that. So the addition and subtraction, just like vectors, if you were adding, you add the components. You add the real components first, then you add the imaginary components. For subtraction, you subtract the real components and then subtract the imaginary components. So it's pretty straightforward so far. For multiplication, it's going to be more convenient to work with the exponential form. So let's consider z1 times z2. So z1 in exponential form is going to be magnitude z1 plus j theta 1 times magnitude z2 e to the j theta 2. So the magnitudes are going to multiply, right? It's going to be z1 times z2. And we multiply the exponentials. So e to the j theta 1 times e to the j theta 2 is going to be the same thing as e to the j theta 1 plus theta 2. So now if I were to write this in polar form, right, the magnitude is still going to be z1 times z2, right? And all I have to do for polar form is I replace the e to the j, right? This part I replace with the angle sign, and I write down the phase angle, okay? If you were to do this operation using polar form, right, it might even be actually easier. So let's say we do this in polar form, like this, right? I'm multiplying z angle theta 1 times z2 angle theta 2. Let's actually put some parentheses here. Right, so what you would do is you multiply the magnitudes, so it's going to be z1 times z2, and then if you're multiplying, you add the phase angles. So notice, I mean, as we expect, we should get the same answer, right? Regardless of the form that we use, we should get the same answer. So in multiplication, it's more convenient to either use exponential form or to use polar form. We're going to have the same business with division. In fact, for division, I'm not even going to bother writing it in exponential form. I'll let you guys write that down and practice for yourself, but I'm going to write it in polar form. So let's say we have z1 divided by z2, right? z1 magnitude angle theta 1, and I divide now by z2 angle theta 2. So the magnitudes are going to divide, just like we would expect. However, in this case, with division, you might have guessed, the overall phase angle is going to be the difference of the individual ones, right? So if I do theta, angle theta 1 divided by angle theta 2 is going to be theta 1 minus theta 2. Couple more. Let's consider the reciprocal. I spelled that wrong. Reciprocal. This should be a C. So if I were to take 1 over Z1, for example, right? It's the same thing as writing 1. By the way, any real number, let's say 1, 2, 3, whatever, you can also write it as the real number at an angle of 0. So basically, real numbers are complex numbers, but with an angle of 0. Okay, which makes sense, right? If theta is 0, that means that the vector is lying completely on the real axis, which means it's a real number. So I can write this as 1 angle 0 divided by Z1 angle theta 1. So in other words, the magnitude is going to be 1 over Z1, and the phase angle is going to be negative theta 1. Finally, we have one last operation, and this is specifically for complex numbers. It's something called the complex conjugate. The complex conjugate, if I have Z1, right, and I want to find the complex conjugate of Z1, I write it as Z1 star. And basically what I'm doing with the complex conjugate is I'm taking my imaginary part and making it negative. That's it. That's what the complex conjugate is, right? So the original vector, or I should say the original complex number, was A1 plus JB1. The complex conjugate is the same thing, except I replace this minus with a negative sign. So all that complex conjugate means is a very long phrase, right, with fancy words. All it means is make your imaginary part negative. That's it. You just take the negative of it. If you were in polar form, right, nothing happens to the magnitude. However, that minus sign, all it does is it affects the phase angle. So if you had a polar form, for example, let's say I had, let's call this, I don't know, let's call this 3 at an angle of 4. If I wanted to take the complex conjugate of this number, right, it's going to be 3. However, all I have to do is put a minus here at the 4. That's it. That's what it means. Just put a minus in the phase angle, or put a minus here in front of the imaginary number. That's it. That's all it means. When I've learned complex numbers, I think of it like the evil twin of your original complex number, right? If you ever know, if you know Spider-Man, right, you have Venom as the evil arch nemesis of Spider-Man. This is exactly the same thing, right? It's the negative version of your original complex number. So that basically summarizes, in a nutshell, all you need to know about complex numbers. And from here, we can talk about phasors and impedances and so on in class. Thank you.